Okay, so we are continuing in sections 3.5 and 3.6, which is really all of chapter 3 at this point, and this is the second page in that example packet. So we have a rubber block. It's subjected to an elongation of 0.03 in the x direction, and its vertical faces are given a tilt so that theta equals 89.3 degrees. Determine the strains at x, y, and okay. So you have to understand this is normal strain, this is change in length. This is shear strain, it is change in angle. So again, we have a lot going on. If I have stress equals P over A, then I have stress equals E times strain. I know that strain equals change in length over original length, and I know that Poisson's ratio is that lateral strain divided by longitudinal strain, okay? And I also have that shear stress is V over A, so something's got to be sliding across the top to cause that. And shear stress is related to shear strain with our shear modulus. And we have that shear strain is equal to pi over 2 minus theta prime, okay? So it's just a matter of understanding. When I look at this, I am told along the x-axis, okay, it has an elongation of 0.03 on the x-axis. So if I want to know the strain, okay, the strain in the x direction, it's going to be important to understand that. So in the x direction, my original length is 4 inches. In the y direction, okay, my original length is 3 inches. Ow, sorry about that. Okay, so if I think about Poisson's ratio then it's talking about the strain that's in one direction compared to the strain in the other, okay? If I'm making this longer in the x direction because I'm skewing it, it is going to become shorter. I can still use this relationship. So let's get started. Strain in the x direction. What is strain in the x direction? It is the change in length, okay, over initial. It is length final minus length initial over initial. I've been told that there is an elongation of 0.03 inches. That is my delta. Okay? So strain in the x direction is 0.03 inches divided by my original length of 4 inches. And I get a strain in the x direction of 0.0075 inches per inch. Now, when I go to the y direction, okay, I am given Poisson's ratio, R, because it's a rubber block, okay, got that? So I know that Poisson's ratio is negative strain in the y, strain in the x. So I have 0.5 equals negative strain in the y divided by strain in the x, 0.0075 inches per inch. Therefore, my strain in the y direction, okay, it's going to be negative, it's getting shorter, is negative 0.5 times negative 0.0075 is going to be a negative 0.00375 inch per inch. So here's our strain in the x direction. We're going to box that in. And here's our strain in the y direction. And now we want to know, okay, we want to know our shear strain. Okay, we want to know our shear strain. And if we go back and look at what is shear strain, okay, I can see this is my original angle is 90 degrees. Okay, I'm giving a tilt. See this right here of theta? So I know the shear strain has to be that little component that makes it up. So shear strain in the XY face is going to be equal to pi over 2 minus theta equals pi over 2 minus, okay, minus 89.3 degrees. But we have to think about that we are in radians. So how do we take care of that? Well, I go back to my little circle, and I know that this is 180 degrees, and I also know that it's pi. So that's how I remember, because I also, if I completed it, it's going to be 360 degrees and 2 pi. So degrees needs to be on the bottom for our ratio to work. So I have pi divided by 180 degrees, and we get rid of the degrees. And when I subtract this out, pi over 2 minus 89.3 times pi over 180, I get a positive shear strain of 0.0122 radians. And there we have it. Okay, that's how we are going to take care of looking at these problems. I'll do the next problem in the next example.